So last week, Fortescue announced that they were abandoning their battery locomotive plans as part of their decarbonization efforts to meet their 2030 goals. And it made me curious, why they did this. They have, really nice application for battery locomotives where they are hauling loaded unit trains, you know, from higher elevations to lower elevations down at the port, and then hauling empty cars, back up the mountain. And so it's like, man, this is the best case scenario for a battery locomotive. So why didn't this work? So as part of my efforts at benchmark data and control is I'm trying to develop a user interface around ALTRIOS that I can use to enable people who don't understand how to program but do understand trains to be able to use the framework. So I wanted to use this as a case study to understand what's going on. So I've configured what I believe to be a somewhat representative concept. So I have four 14 megawatt hour battery locomotives, and I know that Fortescue was looking to use two, but there's a portion of the route where they use a couple of locomotives to help push the train up a grade, and then they detach, and then the train goes on down to the port. And this is something that's done for the diesel locomotives today, so it's not anything different. But trying to model infinity train here, I don't have the capability to place locomotives on and off within a single trip. I'd have to do two separate simulations. So I've made the approximation to just four locomotives. I could probably use a lower battery capacity to try to get a better representation of the actual two battery locomotives rather than four times or twice the battery capacity. I've also added some train cars to the types, and so previously I'd had manifest cars with improved aerodynamics. So I added in the unit cars or for unit trains. So we have loaded and empty. The loaded cars are about 150 metric tons. The trains that they were typically hauling on their route had about 240 cars. I stuck with 220 cars because whenever you go a little bit above this, the consist can't quite make it over the grade. So there's another deviation there where it's not perfect, but I think it's a pretty close approximation. I also have added the capability to adjust what the maximum speed is of the train. So I've stuck to 30 miles an hour here. But that is a knob that you can turn, and there does seem to be an impact. So as far as the route, I've added this extra route that I call the Fortescue network. The route that I'm going to be looking at today is from their cloud break mine, which is this red dot right here, down to the port, which is Port Hedland. So down the mountain. If you wanted to go the other way, just switch those. But I've also got a couple other mines in there as well, in case you want to, look at different places within the network. There's some interesting things. So once we have all that entered in, click the refresh button. It'll take a few seconds to refresh. If you're on a slower internet connection, it may take more than just a couple of seconds. This is something that I'm still trying to optimize to decrease data transfer. But we can see speed and state of charge are what I have currently plotted. So we'll open the graph, and you can see that for this particular train, it started out at the mine with 95% state of charge, and whenever it reached the port, it's about 75. So definitely good application for a battery locomotive, and you can see that it maintained the speed of 30 miles an hour for a good chunk of the route, but there were some grades where it was not able to. And if we want to go back, we can go to here, and let's just say we're going to drop this to 20 miles an hour. We'll hit refresh, and then it takes a little bit longer because the simulation is longer because of the lower train speed, and we can open the graph, and we can see that, hey, as it slows down, we have reduced resistance from aerodynamics and better opportunities for regenerative braking. And so it's starting to look a lot like an infinity train that we're ending up with about a 90% state of charge at the end is what the model's predicting. We also have the ability to plot up other things on the secondary, and so you can see the green line here is the elevation of the route, and so you can see as it's going up and down, where it's not able to achieve the speed limit just because of power limitations, but also as it's descending this grade here, that it is able to recharge. So definitely lots to consider here. Lots to improve on my own model of the fidelity of it and what the capabilities are. But I do think it's interesting that I can do this. I've been able to turn this around in just a few days of having the announcement made. The other thing that I would like to point out is this is the structure that is generated by the simulation object, and so there's lots of information contained in here, probably a lot that you don't care about, but you'll notice like here we have this history object. That's going to be the history for the train resistance model, and you'll also notice it like in the consist there's a history object. So anything that's in the history object you can go ahead and plot up, and so we can click anything here that's res underscore, and that's related to the resistance model. And so then if you hit this open graph, it will show you what's the biggest resistance that we're facing, and a lot of it's the grade. It's a really heavy train, so it makes sense, but you can also turn that off and start to look at, okay, what's the next thing? Okay, so we got some curvature resistance in here. We've got rolling resistance, just because the train's moving. So lots to consider, lots to digest on. But wanted to share this with y'all in case y'all wanted to try to gain some more understanding about why Fortescue's made the decisions that they have.